Hi, welcome. Session is called CG&A, Analytics and Applications. My name is Bruce Donald Campbell. I'm Interaction Design faculty at the Rhode Island School of Design and also a visual analyst with the Center for Environmental Visualization at the University of Washington. I'm hosting and chairing this event as department editor of Computer Graphics and Applications, the online magazine. These presenters will each have 10 minutes to present with extra time for questions. There's a 12-minute slot for each. We have 3 minutes of total slippage time available. So I will try to keep that going should we slip in any way. I'd really like everybody to use Slido, which is available from this session page beneath the stream. That's where you can ask questions and you can upvote them. You upvote them by clicking on the thumbs up button that you see next to each question that appears. I will be asking questions of our presenters as we go based on your upvoting. So please take that seriously. We'll give these presenters the kinds of questions that they deserve for all the hard work that they've done. Our first presentation is by Gennady Andrienko. I'm going to let him introduce his cohort of collaborators and introduce his paper now. Thanks, Gennady.
Thank you for the introduction. My name is Gennady Andrienko, and I'm presenting on behalf of my exciting team of co-authors. This paper is the result of international research project where we, as visual analytics researchers, collaborated with researchers from Greece who developed reinforcement learning algorithm and aviation experts from Spain. We developed a visual analytics framework for explainable, iterative optimization of air traffic scheduling. Flights are crossing sectors of limited capacity. The algorithm iteratively delays some flights to improve the balance and of demand and capacity in the affected sectors. The optimization problem we dealt with is known as a more general job shop scheduling problem, where jobs are allocated to sequences of machines with limited capacities. Our goal was to support developers of a reinforcement learning algorithm, enabling them to understand the behavior of the method, and also to support domain experts who needs to gain trust and understanding of how the method works and which results it produces. Based on our understanding of the key concepts such as machines, jobs, schedule, and their dynamics, we defined the system of exploratory tasks at different levels of abstraction, at elementary and synoptic levels. The system of exploratory tasks allowed us to design and develop necessary visualizations, varying information content and level of details of different aspects of the data presented in different displays. Our solution offers to look at different aspects and relationships between them from multiple complementary views at different levels of abstraction. And in the next slides, I will present in more details with different complementary views. So the first one is the process view, where we aim at enabling understanding of how the key characteristics of a schedule change along the sequence of optimization steps. We call a situation when sector load is over its capacity as hotspot. And having these hotspots, we are very interested to understand how they develop over time, over steps of a learning algorithm, how many different machines or sectors have hotspots at different steps, and how this progress over time. What is the total duration of flights accumulated from one step to another, and how many different flights have different have delays in different ranges of time? This is shown in 4 corresponding blocks of this display. The second important display is the schedule view. It allows to see which hotspots and delays are involved in different versions of the schedule. So here we have 3 steps of a algorithm shown. Step 0 in the beginning on the left, one of key steps in, within the method, step 15 in between, and the final solution at step 144. So we have 3 blocks explaining different optimization steps, and the user may have as many blocks as he wants. Each table in one block represents airspace sectors by columns, and rows correspond to time intervals of the day. Cells show counts of flights and statistics of air delay by segmented bars. So these gray bars show how many flights are present in each sector at each time moment, and different shades of gray represent delays for these flights, from no delay by light gray to hard delay in almost black color. If a case that the demand of the sector is over its capacity, a hotspot is detected, and this is highlighted in red. In the beginning of the simulation, at step 0 on the left, flights have no delays, but many hotspots are present. At a later step, shown in the middle, the number of hotspots is reduced at the cost of delaying some flights. In the final solution, on the right, all hotspots are resolved, but delays have increased further. But the timetable view answers the question, how do individual jobs of flights progress through a sequence of machines or sectors, or how flights go through sectors of the airspace. This view is focused on the user's selected airspace sector, which is shown in the center of the display. Upstream and downstream sectors connected by flights are shown with the dynamics of sector loads and indication of hotspots and how long they happened and how severe they are. This display can also be used for comparing two multiple versions of a timetable as shown on the right. Another view, job evolution view, explains what changes have been applied to a given job plan during the optimization process. The colored bar on top represents iterations of the algorithm, with blue cells indicating delays added to the given flight. The dotted lines in the bottom show how the flight crosses different sectors in different variants of the schedule, accumulating delays and shifting from left to right accordingly, and sometimes even changing the sectors of the airspace. The proposed combination of 4 complementary views enables comprehensive understanding of the model's behavior and answers the following analysis questions at elementary and synoptic level, namely, how the key characteristics of a schedule change along the sequence of optimization steps, what hotspots and delays are involved in different versions of the schedule, how do individual jobs progress through the machine sequence or through sectors of the airspace, and what changes have been applied to a given job plan during the optimization process. To summarize, we defined a system of analysis tasks that allowed us to design a combination of several interactive visualizations that enable model developers to examine the behavior of a model at different levels of abstraction. And this makes the model transparent to users, explaining model outputs and increasing the trust of domain experts. Thank you, and I will be very glad to answer questions.
Yes, thank you very much, Gennady. We don't have any questions in the Slido, but I'll keep watching in case anybody has a question to ask. I just want to say I read the paper and found it really insightful. As I was reading it, a whole bunch of ideas of related applications came to mind. I found the information very easy to see and understood the hotspots that you mentioned and how valuable. I can imagine that being very valuable as complexity rises in these job scheduled processes that you're providing software for. I don't know if any of your co-presenters have a question. We still have 2 minutes. Would anybody like to ask a question of Gennady?
Thank you for your kind words.
Do you have any questions for your co-presenters? Anything specific you'd like to ask? No? Okay, well, we'll move on to the next presentation, if you don't mind then, and maybe we'll get questions for a future presentation so that we can have time to do so. I thank you again for your presentation. Our next presentation is by Tobias Günther, and I will let him introduce his team and the title of his talk. Hello, Tobias.
All right. Good. Yeah, thank you so much for the introduction. Hello, everyone. My name is Tobias Günther, and I'm very happy to show the work of Simone Schaub-Meyer, who developed this system here back in her days at the Media Technology Center at ETH Zurich, together with one of her students, Nicholas Ingulfsen, who wrote his master thesis on this topic, which was back then supervised by Markus and myself. Yeah, so as the title says, News Globe, so this paper is about news. And traditional news agencies are competing nowadays for digital audience, and therefore online news portals explore new ways how they could provide their news content to interested readers. And usually when you look at news websites, they are built so that you can only focus on the very newest headlines, which reduces an article's potential lifespan quite significantly. And this is a missed opportunity to discover relationships between news or to see how stories around a given topic evolve spatially or temporally. News articles typically contain metadata that is not necessarily obvious to the reader, such as simple information like publication dates or the news categories that it can be sorted in, links to other related articles, but also more content-specific information such as named entities or, as it's encircled here, geographic locations. And such information can be quite useful to structure and filter such a dataset. So the users of our application are online news readers, which includes both a general audience who wants to read about current news and how they relate spatially and temporally, as well as journalists who might want to explore a collection of news articles in a more structured form. For the design of the system, we phrased a number of requirements. First, we want to support various input sources, such as articles from the BBC, from Reuters, and other news sources. Second, there are thousands of articles appearing around the globe, which we want to display without overdraw and clutter. Third, there are cross-references between articles, which our readers should be able to follow, to explore how they are connected. Fourth, each article has a timestamp, which allows for the exploration of how information is spreading over time and how topics evolve. Fifth, we want to use the metadata to filter selected and maybe related articles. Six, the system should also provide access to the article details, of course, such as the headings, the categories, a brief summary, and also, of course, the full article itself. And lastly, we want to support the usage of desktop and tablet devices, which put some computational constraints that we need to meet in order to enable real-time experience. Our visualization application consists of two components, the globe visualization in 3D and the user interface, which is layered in 2D on top. And in the middle of the screen, you see the globe visualization itself. Below, there's a timeline that expands along the bottom of the screen where you can filter temporally. The left-hand side allows for filtering by categories and by tags, so you can also search by certain topics. On the right-hand side of the screen, we have then the detailed information on the selected article, including the categories, tags, referenced locations, linked articles, etc. The menu bar on the very, very left gives access to a replay mode, to a live feed, and also to some settings. And all the UI elements that you see here and the user interactions are adapted for both desktop and tablet devices. So we have pinch and swipe gestures and all that. Yeah, we developed this system using around 45,000 news articles from a local news website, 6,000 news articles from the BBC, and 5,000 from Reuters. And all the news articles here are from 2019. To support the news data coming in from these different sources, we had to implement a data pre-processing pipeline that transforms the raw article data into one common format, and you see the entries for that here on the right. For tagging and classification of the articles, we process them using a natural language processing API, which is called TextRaiser, and that classifies the text into a set of categories and also subcategories from the IPTC Media Topic News Code taxonomy. And this includes things such as economy, health, lifestyle, sports, disaster, etc. Additionally, it also gives us location tags with which we perform a lookup in the OpenStreetMap database to find a geographic coordinate for all of the articles to have, so that we also have longitude and latitude coordinates. So each article references now a set of these locations, and we have more than 17,000 unique locations in the system. To add all the locations in, we incorporate here an agglomerative hierarchical clustering, and we see here the clustering for locations in Switzerland on the right. The level of detail adjusts then automatically to the distance of the camera. So the size of these individual spheres here shows us how many articles are contained in these clusters, and also the number of articles is color-coded in a green color map by country on the globe itself. Picking a location then gives us a preview of its associated articles, and then selecting one of these articles visibly connects to the reference locations. And so we can explore the storyline a bit further. It also shows all the meta information on the right, such as the categories of the article, as well as tags that we can use to also search in the article. Yeah, below of this, a histogram is shown that gives us the temporal distribution of articles over time. And this is a scented widget, so you can use this also to find interesting time ranges where a lot might happen on a specific topic. At any time, the user can switch to a pie chart visualization that shows the distribution of article categories for a given location. And while some regions here are largely covered with articles such as conflict or politics, others are more balanced with news on economy, sports, lifestyle, and so on. So it depends a bit on the target audience, what that audience considers newsworthy from other countries around the globe. By applying a tag filter, we can also view articles on a specific topic. For example, here we select soccer, and this, in this case here, gives us articles mainly categorized into sports and conflict, interestingly. To explore the temporal evolution of articles and stories, we can switch to a replay mode where the individual articles appear one by one, and we see this with little icons flying in from the top. And also in live mode, we can likewise see articles come in. The color of these little icons here encodes the number of articles. We added color gradients to the connecting arcs to show the direction of the connection, and we also added shadows to improve the depth perception. For automatic camera animations, the camera position was restricted to a sphere. We can look at an example for this here. Starting from Buenos Aires, we select an article that addresses climate protests around the globe. By selecting one of the reference locations, our camera automatically navigates towards this place, in this case, Sydney. We deployed the system on PC and tablet, and to achieve high frame rates, the filtering operations needed some caching to propagate the state updates efficiently, and we used a view-dependent level of detail for the country boundaries and for the geometry to meet the real-time constraints. To evaluate how well our tool meets the requirements, we conducted an informal user study with 10 participants performing an interactive exploration using our tool. First, we explained how the tool works, then they could try it out for 10 minutes. And then the participants were asked to solve 7 tasks, for example, finding the most frequent category in a certain region, or the time when a certain topic started to occur, and so on. In the table on the right, we can see the response time of the participants in seconds. And the timings are grouped here column-wise by task and are sorted by time for each question in increasing order. And it can be seen that most questions have been answered correctly in a short time, which is shown in blue. And once help was needed, which is shown in yellow, then participants tended to take a little bit longer to answer the question. We hinted which feature to use not earlier than 25 seconds, and only when they were lost and didn't know how to approach the problem. Wrong answers are shown in orange. Yeah, based on the feedback that we got, we found that the temporal exploration worked well. For the spatial exploration, it takes some geographical knowledge, which can be a problem. And the color coding of the countries itself was also not very intuitive. And so later in another iteration, we added also some color maps to explain things a bit better. Yeah, more details on the evaluation can be found in the paper. So in summary, we presented a method to visualize geolocalized news articles. Global scale, we developed a 3D globe visualization for article exploration. With aggregative hierarchical clustering on the locations, the visualizations can adapt its level of detail based on the user's viewpoint, and several filtering options were provided to search by a specific topic, category, or time frame of interest. And we optimized the performance critical parts of the application to achieve interactive frame rates on both PC and tablet. In the future, it would be interesting to focus on how news stories evolve over a collection of articles, for example, to see how certain storylines start branching. That could be very interesting to explore. Yeah, thank you very much for your attention. I'm looking forward to your questions.
Hey, that was great, Tobias. Very great. I like that very much. You have gotten some questions in Slido, which is very useful for me. The first thing that was mentioned, they said it's a very cool visualization that you guys have created. I want to tell you, when I was reading the paper, I personally use an app that's online called radio.garden, which lets you go spin the globe and go into all radio streams from all over the world. Nice. And I really get a sense of cultural differences. And I think it's really useful to be able to travel geographically and get a sense of that. So I could see myself using your app if it was available. And I think that's probably a common feedback you get.
Yeah.
Let me ask one question that came from the Slido. One participant was wondering why you decided to use a 3-dimensional globe map as opposed to just a 2-dimensional map.
Yeah, so the 3D globe, of course, has this problem that it only shows you half of the globe, right? So one half is not visible. When you have only locations, only positions, I think a 2D map is also a great option. In our case, we had these arcs that are connecting the different locations, and it's a bit tricky to decide what to do when the arc has to go around the map. Yeah, if it exits on the right, it has to come back on the left. Do you draw it over the entire map? Then it would create a bit of clutter. Or if the shortest path actually goes over the pole, that's also a bit inconvenient. But yeah, so in the end, building it with 3D version was for that reason. Let's say it's one of the reasons, right, for the edges. The other is also it's more fun to build it in 3D. But yeah.
I agree with that last thought. I'll make another quick question. We only have a minute to answer it, but one other participant mentioned that news stories have a photo with strong visceral engagement. How might you bring many news photos into your application?
Oh, that's a really good point. Yeah, because you would need space for this, right? Yeah, that's, I think if you have a small screen, this will be very challenging. If you have a larger screen, you might have some opportunity to place interesting images on the map. Then it's an interesting layouting problem, where to exactly arrange them and connect them to the location. Yeah, sounds great. Would be nice to add in.
I understand the interest in having visual connections to our news. So
yeah, absolutely.
Good question.
Yeah.
Thank you for that question. And thank you again, Tobias. We're going to move on to the next presentation now. We have Mahsan Nourani, who will introduce her co-authors and present her paper. Hi, Nourani.
All right. Okay, can you hear me and see my slides? Oh, yes. I guess I take that as a yes. So thank you for the kind introduction. My name is Mahsan Nourani, and I'm here on behalf of my co-authors to present our paper that was originally published in a special CG&A issue on explainable visual systems. So consider traditional classification problems where a single label is assigned to every given instance, like what you see in this slide. Now, multi-label classification models instead work with the vocabulary of labels and detect all the applicable vocabulary per instance. This approach is central to applications like visual activity recognition, which is also the focus of this paper. In this context, we divide the vocabulary into 3 types of actions, objects, or locations based on how they contribute to the activity. So to extend activity recognition to videos, then you will have to turn this into a multi-label classification problem per each frame over time, where each activity component and combination of those components influence the upcoming frames. And so when you want to deploy such a complex deep learning model in the wild, you need to iteratively analyze and analyze it in order to improve the performance and fix the problems that it comes with. And in this talk, I'm only focusing on the problem of debugging a model. And by debugging, I mean detecting the errors and reporting or recording them before being able to actually take action and fixing those problems. So what types of problems are we thinking about? So there could be problems that are focused on particular frames. For example, false positive errors, such as some item or some vocabulary label is detected by mistake, or false negative errors, that something that should have been detected is not detected, for example, cutting board here. Then you can go one level higher and discuss and try to find errors that can happen between two frames within the same video, despite the fact that these two are temporally connected and the activities detected in one can influence the activities in the second one. In this example, you see magically after a few seconds, pineapple is detected as a potato, which is a temporal error. You can also take it one step further and look at systematic errors, which are problems within different videos that kind of persist. For example, if the model cannot detect a cutting board between two different videos, then you can try and dig deeper and see, hey, is this a problem that keeps happening? And so why is the model not able to detect cutting boards? So if you want to try to find these problems and debug these models based on these errors, actually this becomes a very challenging problem because you have to look at each frame and then also look at them temporally. And also for each of the data, like inside the data set, when you're training a model, you will have multiple videos. So based on the number of data sets, the number of labels in your vocabulary, the size of your data set, and also length of each video, the debugging can become exponentially hard. We also kind of propose and maintain the idea that it is actually more effective to, instead of asking people to dig deeper and like try to do a brute force approach and looking at, statistical problems and deep model problems. Instead, we can come up with some sort of visual and explorative tool for debugging and detecting errors within these models. And that is what DETOXER does. So I'm going to quickly go over some of the elements of the interface in our design to try to address some of those error finding goals. So first of all, to give an idea of kind of like what is the performance of model overall and how what are the current stats about the model, we provide this global information panel, which includes false positive, false negative errors and accuracy across all of the videos within the data set. We also provide rates of false positive and false negative errors per all of the videos again, but instead for each of the particular labels in these two types of bar charts. So even a quick glance here can show you that the model has a makes more false negative errors, so that kind of can lead to more investigation. But you can also compare an element vertically because they're aligned and see, oh, maybe for example potato has 50% more false negatives or has false negatives 50% of the times, so that is an avenue of search, right? Like I can start my search by looking at potatoes and why it's being missed. And it could be a systematic issue. Then we provide a view with the list of videos, and for each video, we provide top detected components by the model within that video, and also the same rates of false positive and false negative errors per video. And so looking at this quickly can help users identify which of the videos the model is struggling with more. And here, as an example, the third video has the highest rate of false negatives as opposed to the other videos, which could be a good exploration starter. And now if the users want to look for more problems more on an instance level, I guess by instance I mean frames, or temporally, we also provide a view for each video that includes heat maps or temporal heat maps. So we display one heat map temporally for each label within the vocabulary. We assign one color for each frame within the video. And so the warmer the colors are, the more confident the model is about that label appearing in that frame. These heat maps can either be considered separately for each of the vocabulary items, or in combination to form an activity and try to investigate whether that activity is happening or not. And so also this kind of information can help users decide which parts of the video to look at to analyze for more detail. So let me demonstrate this quickly in an example. So looking at the false negative bar charts, I can easily see potato and cutting board have both high levels of false negative rates. So I can go to the left side and try to find a video that has those elements. Upon looking and clicking on the video, I can look at the heat maps and compare, for example, cut and cutting board. And immediately I see that there's very low confidence for cutting and cut and cutting board in that segment of the video. So that's a false negative. And I can also look at these instead of temporally, just look at frames in particular and try to find those errors. If you want to look more, learn more about this use case, there's a video in our supplemental material. I encourage you to check it out. We also evaluated the DETOXER application through two means. The first one was a user study with novice users where they were kind of interacting with the model, think aloud approach, and then followed by an interview with the researcher. And we also did an expert case study with the ML engineer who was our co-author on this paper to show how this system can be used by an expert. Again, not going into details, I'm going to highlight quickly some of these findings. In general, novices loved heat maps, those temporal heat maps under the videos. They significantly used them more often than any other components of the interface. And they also, it goes hand in hand with the fact that they focus a lot on finding instance level errors per video. We also were able to find a lot of model issues. The novices were able to find a lot of model issues regardless of how or what types of issues they were focused on. And actually, in 20% of the times, they started by investigating instance level problems, and they inspired by that and finding errors locally to go find systematic errors because they started noticing patterns of errors that are happening between videos. The second case study also is outlined very well in the paper and also in the supplemental material. So I encourage you to take a look at it. Our AI expert looked at two separate case studies with kitchen activities and wet lab activities and managed to find errors and issues based on what we described earlier, but also additional errors that were not part of the original design and also are supported by this application and the design, such as persistent-based errors, error rules, and confusion pairs. So to conclude my talk, we designed a visual and interactive application for debugging active recognition in videos. This approach and application is domain independent as tested. And also it's open source, the application, and the visual analytics prototype is available on GitHub. And there's also a demo on our website, so please check it out. We also evaluated the approach and the tool with two types of users with different types of expertise. And we kind of show that such an intuitive and visual kind of approach for debugging actually helps specifically for novices. And I want to argue for a second that it might work to give out and crowdsource those debugging factors to novices, even though they don't have necessarily technical expertise to understand the inner workings of the model, and that way we might be able to offload some of the error seeking that are more technical, or even refining those errors to AI experts. With that, I would like to thank you for attending my talk, and if you have more information, or if you need more information about the paper, please check it out. I'm also going to shout out that I am hiring this year for both a postdoc and interns for summer. So check my website out, and I will take questions now.
Thank you, Mahsan. That's a great paper, one that was interesting to me because I am very curious about how these models work and what tools are available to look at the inside of them. So I think that's great work. It's not my area of expertise. We do have one question from the Slido service. One of the attendees says that the heat maps are great. How do you address the ordering of the rows? Because this has impact as to the understanding of label jumps, correct?
Label jumps?
This impacts the understanding of label jumps, correct?
Oh, label
I don't
jumps.
know what that term.
Oh, yeah.
Yes.
Yeah, actually, that is a great question, and I think that I want to address, or I want to highlight that this is a prototype and there's a lot of areas for improvement. So we just had a set order for the highest. So the order was like based on the highest amount of detection for each of the labels. So if for example cut was detected most frequently in the video, we had them always appear at the top, and then the low prediction ones would go to the bottom. But I think there is potential for allowing users to interactively, pin the activities or actions or any of the labels to the top, or try to reorder them. Or if you want to even go overboard, you can try to automatically move the heat maps around once you as the video progresses. But that's a great question, and hopefully future researchers can work on that.
Wow, thanks for that answer. Great. Another applause, and we will move on to our next presenter. Our next presenter is Xiaoxi Wang. I'll let her introduce her fellow paper writers and the name of her title of her paper. Hello, Xiaoxi.
Thanks for your kind introduction, Bruce. My name is Xiaoqi Wang. I will present our paper called An Interactive Knowledge and Learning Environment in Smart Foodsheds. This collaborative effort comes from Ohio State University, University of Wisconsin-Madison, UC Davis, IC Foods, and Texas Advanced Computer Center. The Internet of Food is a rapidly developing field in smart foodsheds, which involves creating a knowledge graph about the environment, agriculture, food, diet, and health. This can improve the current food system for increased food sustainability, health, justice, and delight, as well as facilitate many downstream tasks such as information retrieval and food flow data analysis. In food systems, however, there are several challenges for domain experts to interact with the knowledge graph in smart foodsheds. First, it is challenging to define standardized ontologies to have a unified environment for data exchange. Second, querying information from knowledge graph can be done through structured query language such as Sparkle. It can be quite difficult for those who lack such background knowledge. Third, with a larger amount of information queried from knowledge graph, efficient visualization is necessary to display data patterns effectively. To address these three challenges, we propose an interactive knowledge learning environment. Our key idea is to identify three essential programming languages for these challenges that arise in different interaction tasks. We then design several components to automatically generate or transform those languages to help users to perform the task. Finally, we develop a data flow system to achieve the environment where user can drag the predefined component and connect them to build their different analysis pipeline. The first component is ontology definition. The ontology definition defines different types of entities and their relationship within the knowledge graph. This is essential not only for users to understand and navigate the graph, but also for machine to automatically generate SPARQL queries. Ontology definition can simplify the process of data retrieval. To structure and define this component, we use LinkML, which is a flexible modeling language. It allows us to specify the data schema in YAML format, which can be easily converted into other formats. As a result, we can ensure the adaptability across different schema representation. We first propose an ontology template to define any knowledge graph. Then we develop a parser that processes any LinkML defined ontology for a knowledge graph. This parser converts the ontology into the graph structure with some predefined filters. Users can interact with the graph and apply different filters to the graph. Then all interactions are automatically translated into a SPARQL query for efficient information retrieval, which thus minimizes the need for manual effort. As the final step, we actually execute the generated SPARQL query to retrieve data elements from knowledge graph. Since applying through query results row by row is time-consuming and less effective, we actually use visualization chart to enhance data understanding. To improve explainability, we leverage rule-based visualization recommendation. By taking the tabular data as input, we transform it into Vega-like grammar, which includes both visual elements and data specification. It involves several steps. First, we identify the data type in each column using regex. Then, given the predefined mapping rule, we determine which charts are supported for identified data type and select valid chart as candidate. Finally, the Vega-like specification is rendered into chart, which user can view and download as figure. We've developed a highly flexible and scalable data flow visualization system. This system allows users to build and customize data analysis pipeline through an intuitive interface with two main panels, the component list and the edit panel. As shown in the right figure, the component list includes a variety of pre-designed components that a user can easily drag and drop in the pipeline. This component covers key functions like loading data, analyzing data, and visualizing the results. Each component comes with a predefined functionalities and input-output specification, which make it easy to connect to component and ensure smooth data flow. The edit panel is where user can add or remove components and link them together to create complete analysis pipeline. This flexible system enables users to construct their own custom workflow for data analysis, while enhancing both efficiency and scalability. We have done several evaluations. First, we evaluated the performance of our SPARQL generation algorithm by comparing it with ground truth SPARQL query, which were manually created by our domain expert. Also, we have conducted a systematic comparison between our system and the seven most related systems that are introduced in the related work section. The comparative results demonstrate the unique strengths of our system and its potential as a valuable tool for knowledge graph exploration and analysis. Next, I will show a video to demonstrate 3 different use cases of our system.
Use Case 1, Partner Finder in the Smart Food Shed. Our user, Alice, wants to find possible partners in the food system. She first drags a data loader to load Peapod link ML file and vocabulary file. Then she connects it with an ontology filter to create the ontology of Peapod. Later, in order to find target partners, she first adds the filters of use case and position type. Then she lassos the entities of interest. Our ontology filter will automatically generate the query based on these operations. She later drags a query editor to check the generated Sparkle query. Also, she connects a KG querier to fetch data from the Peapod knowledge graph. The output can be displayed through a table viewer. From there, Alice finds possible partners to collaborate with. Our second use case is how to visualize data automatically. First, Alice selects a data loader to upload a local CSV file. She connects it with a table viewer to display and filter the tabular data. Then, she adds a table visualizer in the pipeline. It will generate a set of candidates and randomly render 4 charts to display data patterns. We further allow users to download pictures and check the specifications of the chart. Our last case shows how to combine the KG query and visualization in the exploration pipeline. Suppose we have a domain user, John, who knows how to write Sparkle queries. He can load in a query editor and directly write queries in it. Then he passes the query to the KG querier to fetch data from Microsoft Academic Knowledge Graph. Once the query is finished, he can either connect with a table viewer to display the results. Alternatively, he can load a table visualizer to visualize the results automatically. Use case 1.
Thanks for your attention. I'm glad to answer any question you may have.
Thank you very much for that presentation. I don't see any questions on Slido yet, but hopefully somebody will ask one from the attendees. I wanted to say that your paper was a wonderful paper for me to read because it's such an important subject on so many local and global issues. I was remembering my graduate work, the first graduate work, which was an intensive study of information science back in 1988, 1989. We didn't really have these great presentation capabilities of the computing devices we used. And your work here reflects the best of what I would have hoped for from that perspective. So it was very joyful to read your paper. I don't have any specific questions except to say that it's a wonderful pipeline. Anybody have a question from our fellow presenters? Were you going to say something, Shashi?
Oh, I just want to say thank you and very cool work for your past project.
Nice, thank you. Well, let's move on then to our next. Oh, we do have one question that snuck in. That's good. It says, suppose I can use a personal knowledge graph. What information do I need to prepare in order to use your tool?
Thanks for the question. So the first thing you will need is the ontology definition of the knowledge graph. And definitely the second thing is the raw data of the knowledge graph or the API we can use to query your knowledge graph. I think with that two essential elements, you will be able to use our system directly.
Nice, thank you very much. One other question is, how easy would it be to plug your system into other biz programming tools, maybe like D3?
I think we somehow use D3 as part of our system and like as the low-level programming, but I feel it's pretty easy to plug in if you still want to extend to more functionality using D3.
That's great. That's what I would have expected based on how modular your design is. Thank you.
Yeah.
Okay, next up is Michael Barish. I'll let him introduce his co-authors and his paper. Take it away, Michael.
Yes, you can hear me, right? Perfect. Thank you very much for the introduction. My name is Michael Behrisch, and I'm presenting to you a paper that's called Visualizing Uncertainty in Sets, which was actually initiated in the DAGSTO seminar on set visualization and uncertainty. And I'm presenting here on behalf of my co-authors that you all see over here. So let's imagine making critical decisions where you know that the data might be wrong. So welcome to the world of data visualization uncertainty. And many of the data problems relate actually how several data instances map to each other with respect to uncertainty. So take, for example, genome-phenome interactions in the biofield, or the management of emergency response units during the Hurricane Milton, right? So we investigated how to convey such uncertainty aspects in these scenarios. And so our results of this paper are actually a conceptual framework where we try to bring this entire research on a more foundational level, where we wanted to map actually the types of uncertainty to what you can display in visualizations, in set visualizations. And very importantly, we investigated here several encodings that might be working out very well for the kind of displaying uncertainty with respect to different data types. And so the impact that we want to produce with this entire paper is that we want to drive actually with this work the research on expressive visual representations that are raising the awareness of how different types of uncertainty map to the information in set data. And we want to foster actually the research in this field. So let's look into the set visualization framework. So number one, the one dimension is what kind of information can you display actually in sets? And here it's set membership, set attributes such as, the cardinality and also, proportion of the sets to each other, but also the set element types. And this is very crude, but if you want to go more into detail on this task taxonomy, then to the state of the art in set visualization that had been published in 2016. So what we added on top is this understanding of the types of uncertainty that can be seen in the outside world. So for example, we all know that Venn diagrams work well with certain data, but then there might be also the fact that you have undefined uncertainty or unquantifiable uncertainty, where you know that the uncertainty is there in the data, but you cannot actually measure it. Or you have the other case, the other extreme, where you know from the past that the certainty is even quantifiable because you had historical understanding of it. And this brings us to this uncertainty framework, where you see that it maps a little bit also into the related work of ours over here, which is around empirical studies of uncertainty visualization, general uncertainty visualization and the mapping thereof. And then we even found 4 papers from Valo, Zhu, Gertler, and Sondach that are really doing uncertainty visualizations in set. So let's look at, the baseline, the stuff that is already done in the wild right now. So here are Venn diagrams that is natural for its use for certain data, bipartite graphs and matrices. And these were the base visualizations that we actually took for our assumptions. But let's look into really explicit encodings of uncertainty, and let me guide you through a guiding use case over here. So we are starting a new college, and we've introduced recently the biology class, but nobody will take it. We know that Alex and Ben are taking French classes, and Ben and Chris are taking history classes, and Dana's actually, we are certain about it, that she will take no class this year. But then the uncertainty pops in. So we know that Eva recently joined our team, and she's not decided yet which courses she will take, Frank as well. And for the math class that we recently established, we don't know who's even joining. So what the Venn diagrams with implicit encodings does not allow us to convey this information anymore, because where should we actually put Eva and Frank as a point in that space? Or where should we draw the ellipse for the math class? And so these implicit encodings do not work anymore, but we know that explicit encodings or other visualization settings allow us to incorporate explicit encodings. So in the bipartite graph, right, the way we're styling lines, for example, can help. In the matrix, we can work around, with different cell appearances and so on and so forth. So the main finding over here is that explicit encodings are required for set uncertainty visualization. let's make this example a little bit. And here we have now this. We want to find out whether our students are coming from a domestic setting or an international setting, and this is, certain because if it's given over here, then we can work with even proportions that you see in the second line of. Hi, was I kicked out of the meeting right now?
You're in the
Hello?
meeting, but we took you out of your presentation. So your presentation froze. Did you experience that on your end?
No, I was just killed out of the Zoom meeting.
So I think you
You're
were
still in the
briefly
Zoom.
reconnected, disconnected. So if you just reshare your slides, you should be able to just keep going now.
All right. So
Don't worry, we have extra time to give you. So
all right. So I don't know where I froze out. So I
you were
just
just starting to go over the example of all the ages in the Venn diagram. I think he's still cut out.
Yeah, this seems to be a connection issue on his end. So maybe, I'm not sure. Let's give him a moment, but otherwise I would suggest that we move to the next speaker and try to wrap this up at the end when he hopefully is reconnected.
That's a good idea. I could run the rest of his presentation from video if necessary. Michelle, it's at your end that you're cutting out.
So
Everybody else is able to.
For some weird reason, my Zoom is restarting without me doing anything, and I have no influence on it. This is interesting.
So you try one more time, and if it cuts out again, I'm gonna go with your video after the next presenter goes. Okay.
That's fine. So I'm going to start just over here, right, where we have this scenario of uncertainty of domestic values, and there on top of the certain values that we can easily show in the proportions, we found out that superimposition works well, but interferes with the perception of colors. If we are going to this extreme case that we wanted to look into really the uncertain attributes over here, then we even have to consider how we are treating missing values and uncertain values in the calculation, right? Because it makes a difference whether we say, okay, uncertainty or certainty is calculated as known values versus total values, or known values versus versus the known values plus the uncertain values. So this makes even a humongous impact over here. So this is what I said already before. And then I'm going to cut this short in the interest of time. We also investigated, other visualization layouts over here. One of them that worked best is the matrix view, because it allows us to show this intersection of all possibilities in terms of, the attribute space. We also found out that other visual variables do not work at all, other visual encodings. So the arrow bars are we know that from Corel et al., that they should be treated with a warning sign, but even in the Venn diagrams, they do not even make sense. So here we can actually go a little bit further than that, but we also found that a lot of the visual variables are totally underexplored in this uncertainty field. And here we want to see actually a shout out to the world that we are seeing more exploration in terms of the other uncertainty values from McAkern that he presented in 2012. So discussion and conclusion, we actually found out that many of the studies that are out there are generalized studies, and they do not take into consideration the user tasks and the context that is vital for any visualization of uncertainty. So, and we have not even started talking about, temporal and spatial uncertainty aspects that are convoluting this entire aspect. And here we are discussing this point way more in detail in the paper, so look out for these points in the paper. The perception of uncertainty needs to critically balance, the depiction of the data versus the depiction of the uncertainty. And we have no way even to measure this currently, and we need more effective alternatives for finding out which combination works well. And the general impact that we want to drive with this research is that we want to see on a grounded basis, more research in terms of evaluation that should be considered how we are doing more effective uncertainty visualizations. So with that, thank you very much for your attention. I know I might be a little bit over time, but these are my co-authors. You can download the paper here. And one small thing, we are searching for a PhD in visual analytics, explainable visual rehabilitation in Utrecht. So with that, thank you very much for your attention, and sorry for the technical difficulty.
Hi, Michelle. Thank you for that. Yeah, you dealt with that pretty well. Thank you for your recovery from that. Everything is in the paper, and that's wonderful because the paper is on an important topic, right? Uncertainty. It seems like there's more uncertainty in every day-to-day decision that we make, and you see more and more people struggling with it and trying to ignore it and push forward with results. So any way we can get foundational work there and build up from it and try and get uncertainty as part of our strengths as a population of people around the world, that's great. So appreciate that. In terms of questions, there's no specific questions available for you. We're doing fine with time, so don't worry about that, and go and celebrate your presentation. And we'll move on to the last presentation. So we'll come back around and give applause to everybody. Okay. Our next presentation is from Stan Nowak. I'm going to let him introduce his co-authors and his paper. Take it away, Stan.
Sure. How is that coming through?
If you could full screen that.
Oh, sorry about that. I think
no worries.
Zoom is acting a little bit different than usual. Just 1 second. Okay. All right. Is that better?
Yes, it is. Take it away.
Okay, great. My name's Stan Novak, and I'm pleased to present this work that I did as part of my research internship at Autodesk with my co-authors, Bona Senioro, Lynn Bartram, who's my PhD supervisor at Simon Fraser, Toby Grossman from University of Toronto, George Fitzmaurice, and Justin Mateka from Autodesk Research. And this was part of a special issue on visualization in the wild for CG&A, and the topic was investigating opportunities for visualizations to support architects who are designing with building codes. Building codes are laws that regulate the construction of buildings so that they're safe, accessible, and sustainable, among other factors. Prior to construction, architects submit architectural drawings to authorities who evaluate whether those drawings and plans comply with the building code laws. This process can be really inefficient and can be a huge strain on the industry. Part of the reason why is that building codes are often written in ambiguous language so that authorities have some leeway to judge the unique particularities of any given project that would be pretty hard to anticipate otherwise. As a result, architects spend a lot of time negotiating, interpreting, applying, and communicating about building codes with officials and other parties. Many building codes do follow simple rules and logic and quantitative spatial constraints, and so building code automation has been explored as a way to try and streamline the process. Most often this involves proprietary black box algorithms that produce compliance checklists like the one shown here. And this approach has had limited success in some narrow applications. But this approach kind of fails to consider the role that architects play and the role that building codes play in their process. Architects are liable for compliance with building codes, and so the lack of transparency is a bit of a problem. And the design and check workflow fails to consider the role that building codes play in design explorations. Building codes are not only a way of evaluating a existing design, but are also a constraint on the design process. And so architects have to think about these constraints when they're creating their drawings and plans, suggesting that some kind of feedback could be useful here. And visualizations have provided some form of feedback to aid architectural design in other applications, suggesting that they could be useful in building codes as well. But visualization applications so far have been limited to highlighting places where drawings and models are non-compliant, so kind of fitting in that design then check workflow. So our intent in the study was to identify places where visualization could provide more support that goes beyond just this approach. We conducted 3 participatory design studies that progressively refined our understanding of architects' needs and potential solutions. First, starting with a semi-structured interview study that gave us a broad overview of the problem space, then a survey that checked our understanding and refined it, and then finally a design probe where we synthesized our understanding from the prior 2 studies to explore the opportunities and limitations of potential visualization solutions. I'll only summarize the findings at a high level so you can see more details about these individual studies in the paper. The key findings were that real-time visualization, providing feedback about building codes, could provide some support to help architects design with building codes, giving them the ability to anticipate impacts and explore the space, but only if they address the complexity of building codes as well. And we found that what we called user-driven knowledge management systems that go beyond what is normally considered conventional visualization would be quite helpful in this application. So I'll explain our key findings using the design probes that we presented to architects in the 3rd study because they capture and synthesize the broad understanding that we gained throughout the entirety of these studies. We presented these low-fidelity mock-ups in interviews and had discussions about what opportunities they saw and what limitations these solutions presented. The first design probe and idea I'll be discussing capitalizes on a basic concept of showing the allowance that architects have within their design relative to the constraint. So we show a building dimension relative to some constraint, and that expresses allowance. And then as the building models is updated, you can get feedback about places where it might be non-compliant. So this basic concept is applied to this design probe, which we actually presented to the architects in the interviews. And this is a scenario where architects were asked to imagine themselves designing a school when considering fire safety codes. These codes regulate the minimum width of corridors along a path to an exit and are based on the expected amount of occupants that would be filing out of each room along a path. So as people file out of each room, we represent the progressively increasing minimum threshold for the corridor width using these blue ghost overlays. Each room type has a different occupancy estimate based on its size, where we represent the size of the room, the area as a bar chart, and then the estimated occupants as a strip chart that's aligned, where each strip represents a person. And then on the far right, you see the blue ghost overlay, which represents the minimum corridor width that files into that room. And this is repeated for each room as approaching the path of exit towards the actual exit. An additional markup that provides additional constraints for architects is shown as a green line representing clients' desired room sizes, as well as the door icons that show the occupancy which additional doors would have to be added. As the architects edit the model, the building code implications are shown, and the knock-on effects are shown in real time. So for example, here the classroom is expanded and the architect gets feedback about places where their design becomes non-compliant. Architects thought these visualizations could aid their design exploration and sense-making by showing the available space they have within these constraints. They could anticipate the impact of code and facilitate the design decision-making process, as well as conversations they have around the design. But they also, at the same time, argued that they would need to be able to control how these building code rules are defined. Given how complex, dynamic, and project-specific these building codes can be, architects felt that they would need this level of control. And one architect described a project they had worked on where they tried to automate building code evaluation, and this was only valid for a year before substantial changes had to be made. Architects informed us that this is because even spatial quantitative building codes can be ambiguous, and it's up to the discretion of any authority judging the application of building codes, which can result in a messy process with evolving or changing requirements, which led us to explore some additional solutions that could work alongside visualizations to make this complexity tractable. We explored solutions where additional knowledge can be embedded in the design software, such as conversations with compliance officers, past applications of building codes to set precedent, as well as references to building code laws themselves. These could be retrieved at a later point in time when they become relevant, either during design or during future conversations with compliance officers. This is the actual design probe that we showed to the architects, and while it was generally well received and they felt it addressed a lot of their concerns, they're still skeptical and wary because they're often presented with ideas that are meant to make their job a lot easier, improve modeling, but at the same time create more headache and a lot more work for them. And in this case, this dealt largely with the additional metadata that would have to be added into the design program, the additional documentation that would be required. And this really highlights the complexity of this space. So I want to end by highlighting some broader lessons learned for the visualization community. I want to emphasize how important it is to consider the broader social and technical context that visualizations are intended to do their work in. Visualizations rarely exist in a vacuum, but are often part of these broader contexts where defining, shaping, analyzing data are all closely coupled and coordinated. And considering how visualizations fit in this context is critical. This means not only considering the opportunities for visualization, but also the limitations of visualization. In this particular application, we couldn't treat data as a given or well-defined, and we needed to have visualizations work alongside a broader set of tools to capture the knowledge involved in making sense of, using, and defining data, in this case, building codes. And I think there's many other applications that are similar in this respect. So with that, I'll end and open the floor to some questions.
Thanks, Dan. That was a great presentation. Appreciate your contribution to our session. We have a question from Michelle. Michelle, you want to turn on your audio and ask it yourself? Might as well.
Sure, if I find my audio setup. So we are actually, that was a great presentation. And so I'm actually, working on sustainability topics with architects together, where we incorporate things like green walls, photovoltaics, water management in the building design. So any idea how you would incorporate this into your tools?
Specifically sustainability design. I think one thing that you often see with additional visualizations in these types of applications is usually embedded in the kind of 3D modeling software. And I think there's an opportunity to kind of go to some coordinated displays and show some additional, more abstracted information, which is kind of the approach that we did. And I think that that might be a good approach here as well, rather than just kind of going with the 3D thing, which tends to be very common.
Yes. Yeah. Thank you.
And one more question, which will make our last question of our session. The asker is not sure if you mentioned, but have you looked into combining your approach with large learning models that are trained on building codes?
No, I mean, I think at the time that we were doing this research, LLMs were really kind of getting started, and it's definitely something that is being pursued by various private companies that are trying to facilitate some of this building code review, and they are definitely using LLMs to both help search for and kind of better summarize and understand building codes. But I can't really speak to how effective that has been and how that might fit into a visualization system.
Since you're a practitioner, what's your thoughts on it in terms of your hopes or your concerns, or you think it's a positive direction to the large learning model?
Yeah, I think it is a positive direction for sure. It is one of those things where it's like there's a lot of excitement, and I think we're figuring out what the constraints and possibilities of the system are. It's a bit of a hammer and everything's a nail right now, so we're figuring it out, but there's lots of great use cases. So yeah, it's fantastic.
Great. I'm glad that's a positive for you, because I think it's coming in all our professions, as they say. So let's have everybody join me in applause for all our presenters. You can continue your discussion on Discord. Also note that their email addresses for the presenters is available when you click on their name shown on this session page. Note that Computer Graphics and Applications is an online magazine. All these presentations were articles that were published within Computer Graphics and Applications. I find it useful for spontaneous and serendipitous thought on the subject of computer graphics and applications overall. Most issues cover a special issue that attempts to, a special topic that attempts to represent the taxonomy of the issue, their solutions and research that's being done. Presenters and attendees who have any idea for a special issue can contact Chris Weaver. He's available at cweaver@ou.edu. So that's cweaver@ou.edu. And with that, I thank everybody for what I found to be a stimulating session. It went off pretty well. Apologies to Michelle for that stressful situation of the presentation. I remember one time where they started playing the bagpipes in the middle of a presenter at a live physical presentation, and it threw the poor presenters off completely. They said if they wanted to continue, they were going to have to start over again because they couldn't pick up mid-presentation. And that was stressful as an audience to see as well. So thanks for everybody doing your best. We'll be thinking about all those hurricane victims and future hurricane victims, past hurricane victims, and any extreme weather that disrupts any of our work. When it's not a pandemic, maybe it's extreme weather, right? And so that'll end our presentations at this point in time. Hopefully see you tomorrow at the same time if you want to continue with the CG&A supported sessions. Cheers to everyone. Bye.